I want you to imagine for just a second that you have a tiny, highly advanced pacemaker implanted deep inside the tissue of your brain.
Right, right.
And every single second of every single day, it is, sending out these little invisible electrical pulses to control a devastating disease.
Yeah, it sounds like science fiction.
It really does.
Yeah.
But this isn't a pitch for a sci-fi movie. This is deep brain stimulation, or DBS. And it is it's a literal miracle treatment for Parkinson's disease.
Yeah.
I mean, people with severe debilitating tremors turn this device on, and almost instantly, the shaking stops.
It's incredible to watch, honestly.
But there is a massive catch to this miracle. For decades, doctors have essentially had to use a blind trial and error method to tune these brain pacemakers. They adjust a dial on the outside, look at the patient's hands, and just hope for the best.
Yeah, and it really has been one of the great paradoxes of modern neurology. We knew DBS worked incredibly well, but the precise mechanism of how and, why it fundamentally alters the entire brain's circuitry in real time, that has remained a complete scientific mystery.
Right. I was thinking about it like trying to fix a complex car engine in pitch darkness just by tapping around and listening to the sounds it makes.
That is exactly what it's like.
But that is the mission of our deep dive today. We are looking at a groundbreaking 2026 Nature Neuroscience study by Jiangsun Ren and colleagues that finally brings like a massive floodlight to that dark engine block. They managed to map out the human brain's exact circuitry in response to DBS.
And it is a huge leap forward.
It is. But before we get into the mapping itself, I have to stop right here because I have an immediate burning question. The researchers mapped these brains using a 3 Tesla MRI machine, right?
Yes, a 3T scanner.
Okay, MRI machines use incredibly powerful magnets and heavy radio frequencies. Putting a patient who has metal wires actively firing in their brain into a 3T MRI, I mean, that sounds like putting a fork in a microwave.
Oh, absolutely.
How on earth is this possible without causing severe, immediate harm to the patient?
That is a very valid fear. And to be honest, it's the primary reason this kind of comprehensive mapping couldn't be done safely at this scale until very recently. The breakthrough that made this entire study possible is the physical hardware itself.
Okay.
The researchers utilized a new generation of 3T MRI-compatible DBS systems. Specifically, they used the G106R neurostimulator and L301C quadrupolar electrodes.
Wow. Okay, a lot of letters and numbers there.
Right, sorry. But the magic isn't in turning the magnet down or anything. It's entirely in the design of those wires implanted in the brain. They use what are called helical coils with non-uniform diameters.
Okay, let's unpack this. Helical meaning shaped like a spiral staircase.
Precisely. If you just have a straight, uniform wire, it acts exactly like an antenna inside the MRI scanner.
Oh, wow.
Yeah, it catches the radio frequency energy, heats up, and can literally burn the surrounding brain tissue or even be physically pulled by the magnetic force.
Which is terrifying.
Exactly. But by spiraling the wires and continuously varying their thickness, making them non-uniform, the design naturally disrupts that antenna effect.
Oh, I get it.
Yeah, it scatters the radio frequency energy before it can build up.
So it basically breaks the physics that would normally cause the wire to heat up.
Exactly. It prevents the overheating. There is no dangerous magnetic displacement force, and most importantly, no cellular damage.
Right.
Because of this structural redesign, researchers were finally able to put living patients into the scanner for unlimited safe amounts of time while the electrical pacemaker was actively firing.
Okay, my anxiety about the whole microwave fork situation is officially quelled.
Yeah.
Let's talk about the sheer scale of what they actually did once the patients were safely in the scanner, because the data haul they collected is just staggering.
It really is. It's arguably the most comprehensive data set of its kind. They tracked 14 Parkinson's patients over an entire year.
14 patients.
Yeah, 14. And they did 5 separate visits. They took a baseline scan 1 month before the surgical implantation, and then followed up at 1, 3, 6, and 12 months post-op.
And what exactly were they looking at during those visits? Because 14 people might sound like a small group to someone used to, massive polling data, but the sheer hours of scanning per person is wild.
Right, the depth of data per patient is what matters here. During these visits, every single patient underwent nearly 11.7 hours of functional MRI testing across 7 different stimulation conditions.
Almost 12 hours inside the tube.
Yeah. And on top of that, they did structural MRIs and diffusion-weighted MRIs to track the physical nerve tracks. They also brought in 27 healthy control subjects to establish a baseline of what a non-Parkinson's brain looks like for comparison.
I feel like we should clarify the difference between those types of scans for anyone listening who hasn't spent time in a radiology suite. How does a functional MRI differ from a standard structural one?
Think of it this way. A structural MRI, or SMRI, gives us the anatomy. It's the physical map of the brain, like looking at a satellite image of a city to see where the roads and buildings are. But a functional MRI, or fMRI, specifically resting state and block design fMRI in this study, it tracks blood oxygen levels in real time. When a specific area of the brain starts working harder, it consumes more oxygen, so the body rushes oxygenated blood to that exact spot.
So the functional MRI is like turning on the live traffic view on your Maps app. You aren't just seeing the roads, you're seeing where the cars are actually moving, right at this second.
That's a great way to visualize it. By tracking the blood flow, we can literally watch the brain think and react. But getting that live traffic view introduced a massive technical hurdle.
Because of the static, right?
Exactly. Even though the new helical wires are safe from heating up, an active DBS device is still pumping out electricity. And electricity creates massive electromagnetic static on an fMRI image. It completely obscures the picture.
It's like trying to watch a TV with terrible reception. So how did they manage to see the true brain activity through all of that electrical noise?
They utilized an advanced preprocessing algorithm known as BCompCore.
BCompCore, what does that stand for?
It stands for Background Component-Based Noise Correction. Essentially, this algorithm mathematically models all the physiological and artifact noise.
Like what?
Like the patient's heartbeat, their breathing, and specifically the intense electrical hum of the pacemaker. And it mathematically subtracts that static from the final image.
So BCompCore is basically acting like a pair of high-end noise-canceling headphones for the MRI scanner. It listens to the ambient electrical hum, inverts it, and filters it out so the delicate, true brain signals can shine through.
That is exactly how it functions. And once they had those crystal clear images, they could finally correlate what was happening inside the brain with the clinical outcomes happening on the outside.
Right, because they need to know if the patient is actually getting better.
Exactly. To measure those outcomes objectively, 2 independent neurologists evaluated the patients using the UPDRS-3.
What exactly does that scale measure?
The Unified Parkinson's Disease Rating Scale Part 3 is the gold standard for measuring motor impairment. It tracks the severity of the visible physical symptoms, so the tremors, the rigid muscles, the slowness of movement, and postural instability.
And what were the results?
They were undeniable. When the DBS device was turned on, patients experienced a 51% average improvement in their UPDRS scores compared to when the device was off.
A 51% improvement in physical symptoms. That isn't just a statistical bump. That's the difference between a patient being trapped in a freezing body and being able to walk across a room to hug their grandchild.
Exactly. It's life-changing.
So, stepping back for a second to piece this together for our 5-minute recap. We have a massive data set tracking 14 patients for over a year, utilizing new helical coil hardware that finally makes high-powered 3T MRIs safe for implants. The researchers used a BCompCore noise-canceling algorithm to see through the static, and the clinical results showed a life-changing 51% improvement in symptoms on the UPDRS-3 scale.
You got it. And that robust foundation of data is what allowed them to make their most crucial discovery about how individualized our brains really are.
Which raises an interesting thought for you listening. If you were designing a treatment or undergoing highly invasive brain surgery, would you rather your doctor rely on a group average or a highly detailed blueprint of your own specific, unique brain? Think about that as we move to our next finding, because that leads us directly into the core of this study, a concept called precision functional mapping. Let's unpack this.
Yeah, precision functional mapping, or PFM, is arguably the most revolutionary part of this research. Historically, neurology has relied on standard group average atlases of the brain.
Like textbook diagrams.
Right, exactly. But the researchers here didn't do that. They used an iterative clustering algorithm to divide the cerebral cortex of each individual patient into 152 highly distinct functional regions.
Iterative clustering. What does that actually look like in practice?
Imagine you have a massive pile of mixed up puzzle pieces and you slowly start grouping them. First by edge pieces, then by color, then by the specific pattern on the pieces.
Okay, I can picture that.
The algorithm does this mathematically with brain activity, grouping areas that fire together over and over again until it has perfectly segregated the brain into these 152 individualized regions, which they then categorized into 18 large-scale networks.
And here's where it gets really crazy to me. They tested how reliable these personal maps were over the entire year. To measure it, They used a statistical tool called a dice similarity coefficient.
Right. Think of the dice coefficient simply as a similarity score ranging from 0 to 1. A score of 1 means absolute, perfect overlap.
So when the researchers compared a patient's brain map to their own brain map from a completely different visit months later, the score was 0.88.
Yes, highly consistent. The map held true for the individual.
But when they compared patient A's brain map to patient B's brain map, the score dropped to 0.64. What does that physically mean for us as humans?
It means we are fundamentally neuroanatomically unique. Your brain's functional networks are as distinct and individual as your fingerprints. The average human brain doesn't actually exist in nature.
And this uniqueness becomes a life or death detail when we talk about the VTA, right?
Yeah.
The volume of tissue activated.
Exactly. Let's visualize the actual implantation. The electrodes are surgically inserted into a tiny almond-shaped cluster of neurons deep in the center of the brain called the subthalamic nucleus, or STN.
Okay, the STN.
When you turn the electricity on, it doesn't just hit a single wire. It creates a physical, glowing sphere of an electrical field around the electrode tip. That sphere of energy is the VTA.
But because my brain's wiring is as unique as my fingerprint, if you put that same sphere of electricity in my brain versus your brain, it's going to hit a completely different set of functional networks.
Which is exactly why the trial and error method was so frustrating for decades. And this brings us to the predictive power of the study.
Right.
The researchers analyzed each patient's resting state functional connectivity, or RSFC. This just measures how different parts of the brain talk to each other when the person is lying perfectly still. They wanted to see if they could predict how much a patient's tremors would improve just based on where that VTA sphere of electricity was located in their unique brain.
But wait, how do you even test a prediction like that without being biased by knowing the answer beforehand?
They used a rigorous technique called leave one subject out cross-validation.
That sounds intense.
It is. Essentially, the computer hides one patient's actual clinical outcome. It trains itself on the brain maps and outcomes of all the other patients, and then tries to predict the hidden patient's healing based purely on their scan.
And what happened?
Well, when they used a standard normative group average brain map to make that prediction, it failed completely. It wasn't statistically significant.
Wow. But when they used the patient's own highly individualized resting state connectivity map,
the prediction was highly accurate. They discovered that each patient possesses a specific optimal target, or OT, in their brain. The shorter the physical distance between the actual electrical sphere and that individualized optimal target, the better the patient's physical symptoms improved.
it essentially proves that relying on the average medical model just isn't good enough anymore, especially when dealing with the brain.
Absolutely not.
So if we summarize this shift to our next little recap, we're talking about moving from a generic textbook approach to dividing the brain into 152 unique regions, proving that our functional maps are as individual as fingerprints using that dice coefficient.
Right.
And showing that we can accurately predict a patient's healing based on how close the VTA electricity gets to their personalized target.
It's a total paradigm shift in how we approach neuromodulation.
It really is.
Yeah.
Knowing that standard medical models are based on averages, how might precision functional mapping change other medical treatments you or your family might receive? It's something to chew on.
For sure.
But here's where it gets really interesting. Because when the researchers mapped these unique brains, they stumbled onto a fascinating contradiction involving a recently discovered network called the SCAN.
Right. The SCAN stands for the Somatocognitive Action Network. It's a relatively new discovery that has completely upended our traditional understanding of the motor cortex.
I love the analogy for this. Think of your brain's motor cortex, the part that controls movement, like a massive symphony orchestra. You have the individual musicians, which the study calls the effector networks.
Yes.
These effectors control the highly specific, isolated movements of your hand, your foot, or your mouth. But the SCAN acts as the conductor of the orchestra. It's the high-level project manager. The SCAN doesn't play an instrument itself. It coordinates the entire body's posture, action planning, and movement intentions so the musicians play together.
That's a perfect visualization. Now, in a patient with severe Parkinson's disease, the resting state connectivity of both the SCAN and the isolated effector networks is highly abnormal. The whole orchestra is playing out of tune.
Okay.
But here is the massive surprise the researchers observed. When the DBS pacemaker was turned on, the connectivity of the conductor was successfully normalized. Its functional connections started to look very similar to the brains of the healthy control subjects.
But there's a massive twist here. The specific effector networks, the individual musicians controlling the hand, foot, and mouth, did not normalize. In fact, they got denormalized. They diverged even further away from the healthy control brains.
Right, which is wild.
Wait, why would curing the patient's tremors make the specific hand and foot networks look less normal? That sounds so counterintuitive.
What's fascinating here is what this implies about the biological mechanism of DBS and really the nature of healing itself. Parkinson's disease causes a chaotic, faulty system across the whole brain. Naturally, you might expect a cure to perfectly restore every single individual wire and network to its original healthy state.
Yeah, that's what I would assume.
But that's not what the body does here.
So it's like a factory where the assembly line workers are all using strange broken methods. Instead of retraining every single worker the hand, foot, and mouth effectors, the brain pacemaker essentially fires up a highly competent project manager, the scan.
I love that, yeah.
This manager comes in and aggressively forces the whole factory to produce the right product, even if the workers are still using their weird, abnormal methods to get there.
Precisely. The DBS is overriding the pathological signals by completely normalizing the high-level conductor. In doing so, it forces the lower-level networks to compensate. It establishes a brand new artificial equilibrium that successfully cures the physical symptoms, even though the underlying biological networks remain structurally abnormal.
Wow. Yeah. It tells us that achieving a clinical cure doesn't necessarily mean returning to the original biological state.
That is just mind-blowing. So by fixing the top-level management, the scan, whole system's output is saved, pushing the individual effectors into an entirely new state of compensation. So to recap this part, we have the scan, the conductor, and the effectors, the instruments. DBS normalizes the conductor, but actually denormalizes the instruments.
Exactly.
It's a fascinating reflection on how complex systems adapt. Have you ever experienced a situation where fixing the top-level management solved a whole system's problem, even if the lower levels were still messy? That's what DBS is doing.
It's a great way to look at it.
Now, I want to push back a little on how doctors actually operate this device. We've talked extensively about the resting state of the brain. But what happens the exact second a doctor turns the dial and the electricity actually hits the tissue? Do they just crank this thing up to a 10?
Definitely not.
Yeah.
And to measure that immediate real-time reaction, the researchers used a technique called block design fMRI, or BDfMRI.
Okay, how does that work? Well, instead of just letting the patient lie still and rest, they actively cycled the DBS device on for 36 seconds, and then OFF for 24 seconds over and over again while scanning.
Wait, if the device turning on creates a massive burst of electrical static, how do you get an instant image of the brain reacting without the static immediately blinding the scanner?
That's where the researchers had to get incredibly clever. They used a mathematical technique called sparse noise modeling.
Sparse noise modeling.
Right. Imagine you're trying to record a very quiet bird singing right next to a loud, rhythmic washing machine. The researchers essentially built a highly detailed mathematical dictionary of exactly what the washing machine, the pacemaker static looks like in every possible phase.
Oh, that's smart.
By knowing the static perfectly, they could instantly subtract it the millisecond the device turned on, isolating the true brain response in real time.
And what do they see when they successfully stripped away that static?
They found that turning the electricity on triggers two completely distinct parallel reactions in the brain. It acts on two main circuits simultaneously.
Okay. First, it hits what we call the M1 circuit, which includes the primary motor cortex, the posterior putamen, and the cerebellum.
And how does the M1 circuit react to the electricity?
It experiences massive deactivation. The blood oxygen signal plummets immediately.
Okay, so the M1 gets muted. What's the second circuit?
That is the GP circuit, involving the globus pallidus and the thalamus deep in the brain. When the device turns on, this circuit shows the exact opposite response. Strong activation. The blood oxygen signal spikes.
So the M1 gets muted and the GP gets going. That's a helpful mnemonic. Muted M1, going GP. But let's talk about the actual dial the doctor is turning, the frequencies of the electricity. They tested 3 very specific settings in this study, right?
They did. They tested high-frequency stimulation, or HFS, at 130 hertz. They tested low-frequency stimulation, LFS, at 60 hertz. And they tested variable frequency stimulation, VFS, which alternates back and forth between a 130 and 60 hertz.
Now, earlier we established that the patients saw a 51% clinical improvement overall, but that wasn't distributed equally across all those frequencies, was it? No, it wasn't.
High frequency, the 130 hertz setting, showed the strongest overall clinical improvement. It was the best at normalizing that scan conductor we talked about. So why not just leave everyone on high frequency forever?
Well, if we connect this to the bigger clinical picture, it's because the brain is incredibly delicate. While high-frequency stimulation is fantastic for stopping tremors, prolonged exposure to 130 hertz can sometimes cause the brain to habituate.
Like it gets used to it.
Exactly.
Oh.
Or it can even worsen specific, highly debilitating symptoms over time. For example, some patients develop severe speech impairments or something called gait dysfunction, which is a terrifying condition where a patient is trying to walk, but their feet feel physically glued to the floor.
Freezing of walking.
Yes.
And that's where the other dials, the 60 hertz and the alternating frequencies, come into play to rescue the patient.
Exactly. The researchers discovered that the muted M1 and the going GP circuits have highly specific frequency-dependent responses. The strength of the activation in the GP circuit literally scales with the hertz. It activates a little bit at 60 hertz, more at the alternating variable frequency, and highest at 130 hertz. Because these circuits respond differently to different electrical pitches, neurologists can actually switch a patient to low frequency or variable frequency to rescue their walking or speech when the high frequency starts causing side effects.
They are quite literally playing the brain circuits like an incredibly complex instrument. They are adjusting the electrical pitch to fix a very specific biological symptom.
That's exactly what they're doing.
So if we look at the whole picture of what happens when you turn the dial for our final recap, they use block design scanning to watch a real-time game of neural tug-of-war, seeing the M1 circuit mute and the GP circuit activate.
Right.
And they prove that different electrical frequencies, like 130 hertz versus 60 hertz, can be used selectively to tune out specific side effects like gait dysfunction or speech issues.
It shows us that the brain is remarkably beautifully tunable, provided you finally have the exact map to read.
Which leads perfectly to a thought for you listening. If your specific, uniquely wired brain responds completely differently to 130 hertz of electricity versus 60 hertz of electricity, what does that tell you about the fundamental electrical nature of human consciousness itself?
It's a deep question.
We are, at our core, electrical beings.
And that realization changes everything about the future of neurology.
So what does this all mean? Bring it home for us. What is the ultimate takeaway from this massive data set?
Oh, it means we are crossing a major historic threshold in medicine. For decades, deep brain stimulation for Parkinson's has been an undeniable miracle, but it has been a blind one.
Yeah.
We implanted the electrodes, tweaked the voltage based on what we saw happening on the outside, and just hoped for the best inside. This study by Wren and colleagues proves that the human brain is not a monolith. It is a highly specific, unique, electrically tunable instrument.
We are officially moving away from the era of trial and error medicine.
Exactly, and entering the era of precision, individualized neuromapping. By proving we can safely map these networks in a powerful 3 Tesla MRI, with the device actively turned on, we now possess the literal blueprint to personalize treatment to the exact millimeter of a patient's unique biological wiring.
It is just incredible to think about that tiny pacemaker sitting deep in the dark, finally being illuminated by this massive algorithmic data haul. It feels like stepping out of the medical dark ages.
It really does.
But I want to leave you with one final provocative thought to mull over on your own as we wrap up. Today, we have talked entirely about using this 3T MRI precision mapping to cure the physical motor tremors of Parkinson's disease.
Right.
But we already know these brain pacemakers are currently being tested for a myriad of other things. So if we can now safely map and perfectly tune the individualized electrical circuits of the brain to stop a physical tremor, what happens when we apply this exact same individual mapping technique to psychiatric conditions?
Oh, wow, yeah.
What happens when we can map the unique circuitry of severe treatment-resistant depression or the deteriorating memory networks of Alzheimer's disease? Are we on the verge of being able to literally tune the human mind, isolating the frequencies of our deepest sadness or our lost memories?
The possibilities are incredible.
Think about that. The implications are endless. Thank you for joining us on this deep dive. Keep questioning the incredible world around you, and we'll see you next time.